Good afternoon, everyone, and thank you for joining me here. In this session, I'll walk you through building an end-to-end enterprise AI platform on Azure aligned with Microsoft Cloud Adoption Framework, CAF. Specifically, we'll focus on how to design an AI application landing zone built on top of a foundational Azure landing zone to enable scalable, secure, and production-ready AI workloads across the enterprise. A little bit about me. I am Ehsan Eskandari, a senior Azure consultant specializing in infrastructure and application modernization, data platform, as well as AI platform. I am a Microsoft MVP on Azure category. Been honored to be in the program in last 9 years. I am also a subject matter expert for several Microsoft certification exams, and I lead the Metro Toronto Azure community in Toronto, where we monthly discuss cloud-native solution on Azure and AI topics. Let me walk you through the agenda. We will start with the real-world business problem, walk through the vector and AI pipeline, then examine the reference architecture. From there, we cover reliability, scalability, observability, and finally, security. Problem statement. Imagine millions of documents flowing in from partner every day, and your user expect instant meaning-based answers, not keyword matches. This is exactly the problem we solved: an AI platform on Azure that ingests documents in real time, generates vector embeddings, and delivers semantic search at enterprise scale. It is an architecture to handle real workloads, real failures, and real cost trade-offs. Let me walk you through the 4 areas of our vector and AI pipeline. First, the embedding pipeline. When a document arrives from a partner webhook, it lands in Cosmos DB. Azure Function then generates vector embeddings using our AI models, and they store them right alongside the original content. Everything lives in one place: vectors, metadata, and source text. Second, why vector search matters. Traditional keyword search fails when users phrase question differently than how documents are written. Vector search matches on meaning, not words. So a query like, how do I reset an enterprise admin password, will find documents about credential recovery, even with 0 keyword overlap. We use Cosmos DB vector indexing feature, which is optimized for approximate nearest neighbor or ANN patterns and RU efficient queries. Third, the RAG flow. A user query hits our API, which is hosted on Azure Container App, gets converted to an embedding using the same model, retrieves the top most relevant documents from Cosmos DB, and injects that context into the LLM prompt. The result is a grounded response traceable to enterprise data, not a hallucination. And fourth, enterprise considerations. We handle millions of embeddings with a partitioning strategy, manage model evolution through a re-embedding batch job running on AKS, and reliability and security, which we will talk in next slides. Let me start with a high-level view of the reference architecture for this enterprise AI platform on Azure. At the front, all client requests come through Azure API management, which gives us a centralized layer for security, routing, governance, and policy enforcement. In addition, all calls to Microsoft Foundry services, including embedding generation and chat models, also pass through API management, allowing us to enforce consistent governance, apply rate limiting, and control access across all AI workloads. Those requests are then served by Azure Container Apps, which host the backend APIs for semantic search and updating documents. For retrieval, we use Azure Cosmos DB for NoSQL with vector search. This is where both the documents and their embeddings are stored, allowing us to perform similarity-based search directly against the operational data store. Once the retrieval service gets the relevant result from Cosmos DB, it constructs a prompt and sends it to the Foundry chat model to generate and compile the final response back to the user. For document update, our document update service saves the document in Cosmos DB. To keep the index current, we use Azure Function, listening to the Cosmos DB change feed. When new or updated documents are detected, the function uses Foundry embedding models to generate fresh embeddings and write them back into the Cosmos DB. We also publish document and embedding events to Azure Service Bus, which decouples downstream processing. A worker container app consumes these messages and pushes the data to downstream system as needed. For larger scale initial ingestion, we use AKS to load documents from Azure Storage, generate embeddings in bulk, and seed Cosmos DB efficiently. From a DevOps and operations perspective, all code lives in GitHub. Deployments build container images and publish them to Azure Container Registry. Configuration is managed through Azure App Configuration. Sensitive secrets are referenced securely from Azure Key Vault, and observability is handled through Application Insight and Log Analytics. In the next few slides, I'll zoom into three key areas: initial seeding, user semantic query processing, and the document update pipeline. On initial seeding, first, AKS performs large-scale ingestion by loading documents from Azure Storage account. Next, it calls Microsoft Foundry embedding models to generate vector embeddings at a scale. Finally, both the raw documents and their embeddings are stored in Cosmos DB, making them immediately available for semantic search. For the user query flow, the user first calls the API, which is routed to the retrieval service running on Azure Container App. The service sends the query to Microsoft Foundry to generate the embedding, then perform a vector similarity search in Cosmos DB to retrieve the top result. Then it constructs a prompt and sends it to the Foundry chat model to generate and compile the final response. Finally, the response returned back through the API to the user. For document updates or additions, the user calls the API, which routes the request to document service on Azure Container Apps. This service first updates the document in Cosmos DB. The change then triggers an Azure function via change feed, which generates new embedding using Microsoft Foundry and updates the record. An event is also published to the service bus, where a worker service picks it up and sends the document and embeddings to downstream system. Reliability in enterprise AI system is about ensuring consistent response, continuous data availability, and graceful handling of failures. Reliability can be described using active-active, active-passive, and stamp patterns. In active-active, two or more regions are live at the same time and can serve requests. In active-passive, one region is actively serving traffic and another is standing by for failover. In a stamp pattern, you can deploy multiple independent copies of the same architecture unit. It can be one as active and the other one, when primary region is down, to be provisioned in about less than 1 hour if that's acceptable to your business requirement. Active-active and active-passive address regional availability and failover, while stamp pattern improve cost efficiency in this case. Now, here is more details. We use Azure Front Door as the global entry point, with the private DNS zone supporting private regional resolution across environments. We deploy across 2 regions, prod 1 as primary and prod 2 as secondary, which allows us to support either active-active or active-passive, or a stamp architecture depends on the business need. Active-passive is the simplest and the most cost-efficient option in this case, with fewer moving parts to manage. To maintain data resiliency, Cosmos DB continuously replicate data to the secondary region, enabling failover and improving business continuity during regional outage. Scalability in this platform is about letting each layer scale independently. Container apps scale differently from API and background processing, HTTP traffic for query path, and queue depth for downstream path. In Cosmos DB, partitioning and two-stage retrieval are key to control both latency and RU cost. We first narrow the result set with vector search, then apply metadata and access filters. Azure Functions scale for event-driven ingestion. Foundry scaling depends on quota. We scale out by deploying across multiple regions to tap into separate quota pools. And finally, AKS handle batch re-embedding when model change. In a RAG system, observability is critical because a single request crosses multiple services. We rely on Azure Monitor and OpenTelemetry so we can trace requests end-to-end across functions, container app, AKS, Cosmos DB. Beyond normal API metrics, we also monitor embedding latency, vector query performance, as well as RU usage. That helps us diagnose real issues like RU spike, slow retrieval, or failures in asynchronous processing. Without tracing, debugging an event-driven pipeline like this become very difficult. Security starts with identity, network isolation, and secret management. We use least privilege everywhere. We manage identities instead of shared secrets wherever possible. Core services like Cosmos DB, Service Bus, and ACR are accessed through private endpoints, so the data plane stays off the public internet. Partner-facing traffic is protected through web application firewall plugin in Azure Front Door and rate limiting, while AKS runs a private cluster with restricted egress. Secrets are stored in Key Vault and accessed securely by workload at runtime. The main idea is layer protection. Identity, network, and secrets all reinforce each other. The second half of security is about protecting the AI workflow itself. In RAG, access control must also happen at retrieval time, so users only get answers grounded in documents they are allowed to see. We also defend against prompt injection from retrieved content, and we apply content safety and PII control where needed. On the supply chain side, we scan code and container images, sign images before deployment, and enforce trusted registries. For detection and response, log flow into log analytics with correlated tracing, and Defender helps monitor for unusual behavior. The goal is not just secure infrastructure, but secure AI behavior. And with that, thank you everyone for joining me here. Really appreciate your time, and I hope you found this session helpful. Thank you.